Under these assumptions, the probability of event E is defined as P of E equals the number of outcomes favorable to event E divided by the number of possible outcomes. So, you have learned the lingo of probability. You know what sample spaces and events are. Well, good for you. But you are not ready for the streets of data science yet. The other data scientists out there don't just want to hear words from you. They also want you to be able to compute probability. To compute probability, first you must be able to count. Remember, probability has a numerator and a denominator. You should be able to count all the outcomes favorable to the event and also all the possible outcomes in the sample space. Let's try the chance experiment of rolling a dice twice. There are 36 equally likely outcomes. Let's count them all. Omega equals 1, 1, 1, 2, 1, 3, and so on, and 2, 1, 2, 2, and so on, and finally 6, 5, and 6, 6. Now suppose I ask you to compute the probability of the event. One of the rolls is at least 4. Let's try to count the outcomes that are favorable to this event. If 1, 2, or 3 appears in the first roll, then the second roll can only be 4 or higher. If 4 or higher number appears in the first roll, then the second number can be anything. So let's write down the outcomes that are favorable to the event. 1, 4, 1, 5, 1, 6, and then 2, 4, 2, 5, and so on. And then 4, 1, 4, 2, 4, 3, all the way to 4, 6, and then so on and so forth. And 6, 1, 6, 2, all the way to 6, 6. We can count 27 favorable cases. So the probability of the event is 27 by 36, or 0.75. The above example was a case where we could explicitly write down the entire sample space. In simple cases, we can afford to do that, but you can see it is already getting cumbersome to write and count the entire sample space as well as the favorable cases. What if there were 3 dice rolls? Can you count the sample space now? Let's try writing it down. So omega equals 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, and so on, and then 1, 2, 1, 1, 2, 2, 1, 2, 3. Oof, this is horrible. I don't think this is even worth it. What do we do now? I guess this is the end of the saga. Goodbye, data science. Wait. It's time you learn the first trick. Some smart mathematicians have found some simple rules that you can use to count in these complicated cases. Let me introduce you to the fundamental counting principle. The principle is, if a process is accomplished in 2 steps, and the first step can be accomplished in n ways, and the second in m ways, then the process can be accomplished in n times m ways. Let's try to understand it better with the help of this diagram. As you can see, there are n times m different paths through which you can complete this process. This principle can be extended to processes with more than 2 steps. So in the case of the experiment where you roll the dice 3 times, there are 3 steps. Each can be accomplished in 6 ways. So the 3 rolls can be accomplished in 6 times 6 times 6, that is 216 ways. And your sample space has 216 equally likely outcomes. Suppose you have 6 balls and 4 buckets. How many ways can you put these 6 balls in the 4 buckets? You are allowed to put more than 1 ball in a bucket. So there are 6 steps. Each step can be performed in 4 ways. So this process can be performed in 4 times 4 times 4 times 4 times 4 times 4, or 4 to the power 6 ways. In general, if you have k balls and n buckets, The process can be accomplished in n to the power k ways. Now let's apply our newly learned trick to a probability problem. Suppose your company allows 12 casual leaves a year. If you are choosing casual days at random, what is the probability that you would have taken all your leaves on either a Monday or a Friday? So your company wants to know whether you are abusing the system to get an extended weekend. Well, there are 5 days a week and there are 12 steps, so the sample space is 5 to the power 12 outcomes. Now, if you only take leaves on Mondays and Fridays, this can be done in 2 ways. So the number of favorable cases for our event is 2 to the power 12. Therefore, the probability that all your casual leaves would be taken on either a Monday or a Friday is 2 to the power 12 by 5 to the power 12. That equals 0.000168, which is a very small probability. So if your employer sees that a lot of your casual leaves fall on Monday or Friday, he would know that you've been a naughty boy or girl. Time to challenge yourself. Let's see if you are ready to deal with hard problems like the ones that life is going to throw at you. Suppose you roll a dice 4 times. What is the probability of the event? At least one roll is 2. So it can be that 2 shows up only 1 time in the 4 rolls, or 2 times, or 3 times, or all 4 times. These are all the favorable cases. What is the probability of this happening? Not so easy, is it? Now, if you are an engineer like me, you will probably start writing down each of the possible cases and try to get the entire set of favorable outcomes. But I happen to have a friend who is a mathematician. He says that if the probability of an event is hard to compute, then consider the complementary event. That is, the event that is exactly opposite to the event of interest. So in this case, the complementary event is none of the rolls is 2. This is easy to compute. You see, at each roll there are 5 possible outcomes, which is any outcome except 2. So if the probability of not seeing a 2 in one roll is 5 by 6, same for the second roll, same for the third roll and the fourth roll. There are 4 steps in the process. The probability of the complementary event is 5 by 6 to the power 4. Now, if you exclude all these cases from the sample space omega, we get the probability of our original event. That is, at least one roll is 2. We also know from our definition of probability that the probability of the entire sample space is 1. So to get the probability of our event, we simply subtract the probability of the complementary event from 1. Therefore, the probability of our event is 1 minus 5 by 6 to the power 4. Awesome. I guess you have learned 2 tricks today. So remember, whenever you see problems that ask you to compute the probability of at least one of the cases is something. If the favorable event is hard to compute, try the complementary case and then subtract the complementary probability from 1. It is possible that the complementary case is also hard to compute manually, in which case you are stuck. These kind of problems might interest PhDs. You might also need the help of computers to solve those problems, but you can ignore them for now. Alright, now what if you have a process where the first step can be done in 1 way, the second step in 2 ways, third in 3 ways, and so on up to n steps? How do you write 1 into 2 into 3 into 4 all the way up to n? I don't feel like writing this whole thing again and again. Thankfully, mathematicians use a symbol for this operation. It's called the factorial. It is denoted by the exclamation mark. So n factorial is product of all integers from 1 to n. Another way of describing this operation is through a function. F of n is equal to 1 if n equals 0 or n into f of n minus 1 otherwise. It is only defined for positive numbers. Notice that it is defined in terms of itself. If you have taken any course in computer programming, this function would be very familiar to you. It is a classic example of recursion. In Python language, the code would look like this. If you are not familiar with coding, just ignore this part for the time being. But remember, programming is also one of the tools of a data scientist, so you better get handy with it eventually. The next battle in our saga is near. Do you want to continue our journey? Then subscribe and like. How it is solved. He said, dude, you need to learn permutations.